All right, I just want to send a little video follow-up. I'm going to go over the couple problems we did and then finish going over the rest of them together. All right, so quick little review. This is the formula sheet, all the formulas that you guys have used so far. This is in the back of your book. If you want to look in the back of your book, let me see if I can pull it up here. Right. Actually, I'm sorry, it's Appendix B. So in your books, I think it's around page 336. I think this is a different version, like a different edition than the book that you have, but it should be around page 336, and there's a list of all the formulas. So if you want to put a tab on that so you can have that to refer to, that might be helpful. And then right before that, if you want, this is your Appendix A, and these are the conversion factors. So if you have those memorized, that's great. If not, you can look back at this table when you have to do the conversion factors. And the ones that you guys are working on for class this week, this is the weight equation. The amount of force for weight is equal to the mass of the object times the gravitational pull of the object. So mass times gravity is the force due to weight. Gravitational potential energy is mass times gravity times height. And you might notice that mass times gravity, that's the same as this. So another way to think of gravitational potential energy is that it's the force from the weight times the height. Okay? So gravitational potential energy, if we think of, we talked about like a bucket on the ground, and then a bucket being lifted to a certain height, and then a bucket landing back on the ground. So the instant that bucket comes up, it has the highest kinetic energy that it will have, and the gravitational potential energy is 0. So if I say that this bucket, when I lift it up, it has kinetic energy that is equal to 100 joules, okay? As this is going up, the kinetic energy is going down and the gravitational potential energy is going up. So now at the top, the gravitational potential energy has all of the energy, and the kinetic energy, when it's at the top, it stops. So at the very top, it's not moving, and the kinetic energy is 0, and everything is gravitational potential energy. And then as it comes back down, the gravitational potential energy is going down, and the kinetic energy is going back up. So the instant before it hits the ground again, the kinetic energy is going to be at its max, and that would be 100 joules for this system, and the gravitational will be back at 0. Okay, so all throughout this, as one energy is going up, the other is coming down. And this is showing how energy changes form from one form to another. This is changing from kinetic to gravitational and from gravitational to kinetic. So the formulas for these, gravitational potential energy is equal to the mass of the object times the gravitational pull, and then times the height that it's lifted off the ground. And this right here, this is also the same as weight. So gravitational potential energy is equal to weight times height, or mass times gravity times height. And kinetic energy is equal to 1/2 times the mass of the object times how fast it's traveling squared. 1/2 mass times velocity squared. So these are the two formulas you really need to be using a lot when you're working out through these problems. Sometimes we need to manipulate them. If we were trying to solve for height, we'd have to try to isolate h. If we're trying to solve for velocity, we'd have to isolate v for velocity. Because this is a square, this is a little bit trickier than some of the other ones, and you can actually just look up the formula if it's hard for you to get v by itself. Velocity is going to be equal to 2 times the kinetic energy divided by the mass. All right, so these are the main formulas that we are using for today. These are the classroom computation problems that we're supposed to do together. So water is pumped into a high water tower. So I'm going to draw the water. The water was pumped into this water tower. So now all the water is at the top. The mass of the water is 1.00 times 10 to the 5th kilograms. And then the height of the tower is 240 feet high. And they want us to figure out what is the gravitational potential energy. Okay? So let's write down our knowns. What are we given? So we're given that the mass is 1.00 times 10 to the 5th kilograms. And that's great for us. It's already in MKS units. And then we're given that the height is equal to 240 feet. And that is not MKS units, so let's convert that. So we're going to convert feet to meters. 0.3048 feet in 1 meter. All right, and when we multiply those out, you know what, I'll do it on the calculator so you can watch how to do those. So you can do it in your own calculator as I'm doing it here and then compare. So we're going to do 240 times 0.3048. And we get 73.152. All right, and let's see how many units, and that's going to be, I'm sorry, meters. How many significant digits do we want? Well, we have 2 here. And this one has 4. So we're gonna go to 3 significant digits. We're gonna keep it 1 more than it has because we're still performing calculations. So it's 73.2 meters. All right, and now we want to figure out the gravitational potential energy. So the formula for gravitational potential energy, you might know it, and if you don't know it yet, you can look it up in the back of your book. It is mass times gravity times height, or we could think of that as the weight times the height, because mass times gravity is the same as the weight. So the mass is 1.00 times 10 to the 5th kilograms. And now the gravity is 9.80 meters per second squared. And then the height is 73.2 meters. All right, we'll plug all those in the calculator. 1.00 1.00 times 10 to the 5th times 9.80 times 73.2. All right, and we get 71736,000. 1, 2, 3. All right, and this is going to be, this is energy, so we're measuring that in joules. All right, and how many significant digits should we have? We have 3, 3, 3. But you know what, here we only have 2, so our answer is going to be just reported to 2 significant digits. So 1, 2, and that 1 is getting bumped up. So it's going to be 72 million, or 7.2 times 10 to the 7th joules. All right, so we have a bullet with a mass of 25 grams. It's fired at a velocity of 556 feet per second. And we want to figure out what is its kinetic energy. All right, so we have a bullet. I'll do a little bullet here. We know that the mass is 25 grams. We know that the velocity is 556 feet per second. And what we're trying to figure out is the kinetic energy. All right, so writing down our givens, so that was kind of just a diagram to help me keep track of what's going on here. So I'm going to write our mass is 25 grams. And is that in MKS units? It is not. So for mass, we want to convert that to kilograms. So 1,000 grams and 1 kilogram, 0.025 kilograms. All right. And the other thing they gave us is that the velocity is equal to 556 feet per second. Well, we want to change that feet to meters because we want MKS units. Okay, and if you're not sure what that conversion factor is, look it up in your appendix. And it is 1 foot is 0.3048 meters. And when we plug these into the calculator, so we get 556 times 0.3048, we get 169.466. I'm sorry, 4688. And that's going to be meters per second. And then how many significant digits? Well, it says 3, so we're going to leave this one to 4. So it's going to be 169.5 meters per second. All right, and now they want us to figure out the kinetic energy. So we have to think of what's the kinetic energy formula. Well, it's 1/2 mass times velocity squared. And again, if you're not sure, it's in the back of your book there too. Right, and we already have the mass and we have the velocity, so we could just plug those right in. So it's 1/2 times the mass was 0.025 kilograms. And then the velocity is 169.5 meters per second, and that has to be squared. All right, plugging that into the calculator here. So we get 0.5 times 0.025 times, and now I'm going to do parentheses because this part has to be squared, 169.5 squared. And we get 359.128 joules. All right, and how many significant digits are we going to report that to? We're going to go to 2 significant digits. All right, so that 5 is going to get bumped up because of that 9, so it's going to be 360 joules. All right, for this one, a man lifts a bucket of sand 75 centimeters above the ground. All right, so we have a bucket of sand. This is the ground. So this is 75 centimeters. And the bucket of sand has a mass of 12,500 grams. And they want to know how much work did the man do. Well, we have to remember the formula for work. Work equals the force times the distance. Okay? And the force needed to lift something up. Do you guys remember what it is, the force you need to lift something up? The force needed to lift something up is equal to the force of the weight. So we can think of this formula. The work is going to be equal to the force of the weight times the distance that we're lifting it. All right, so we are given that the mass is 12,500 grams. And we have to change that to MKS units. So we're going to multiply that by, or change that to kilograms. So there's 1,000 grams and 1 kilogram. So this is equal to 12.5 kilograms. All right, and we also were given that the height is going to be 75 centimeters, but we need to change that to meters. So there's 100 centimeters and 1 meter. So 75 divided by 100, that's going to be 0.75 meters. All right, and then weight, the force of weight, FW, that's equal to mass times gravity, right? So the force of the weight is going to be the mass, which was 12.5 kilograms, times gravity, which is 9.80 meters per second squared. And when you plug in your calculator 12.5 times 9.80, we get, I'll plug that in right now. 12.5. 12.5 times 9.80, 122.5, and that's newtons. And we want to change, well, now we have that. Now we, in order to figure out the work, we have to do 122.5 work equals the force FW times the distance. So again, I'm going to give myself a little more room. So work is going to be 122.5 newtons times, and the distance that we figured out is 0.75 meters. And when we plug those in, we're going to get 92 joules. Referring again to the previous problem, after the bucket of sand is lifted, how much energy does the sand have? So I'm going to copy down, and I don't have that anymore. We figured out that the height was 0.75 meters, and we know that the mass was 12.5 kilograms. So when the bucket of sand is lifted, how much gravitational potential energy does it have? Or it's equal to mass times gravity times height. And we know from the last was 122.5. Okay. So the potential energy is going to be 122.5 times the height, or 122.5 newtons times 0.75 meters. And again, that's going to come out to 92 joules. So that's just showing you, so the gravitational potential energy at the top is equal to 92 joules. And if we think about that, the bucket here, the amount of work it takes to lift it right here is the amount of energy that it has. And we're putting 92 joules of energy. We're putting 92 joules of work into that. And in the beginning there, that's going to be equal to the kinetic energy in the very beginning. And then when that bucket is at its top, now there's no kinetic energy and it's all gravitational potential energy. So at the top here, it's going to be 92 joules also. So work going into it in the beginning is 92 joules. The kinetic energy right at the beginning, after the work goes into it, is 92 joules. And then the gravitational potential energy at its top is 92 joules. And then back at the bottom over here, the kinetic energy is going to have the 92 joules again, and gravitational is going to be 0. All right, if the man releases the bucket of sand and lets it drop, what's its velocity the instant before it strikes the ground? So again, thinking of our little diagram here, what is the velocity the instant before it strikes the ground? So velocity, in order to do this, we need to do 2 times the kinetic energy divided by the mass. What is the kinetic energy going to be the instant before it hits the ground? Well, we could figure it out mathematically, but you might be able to recognize now that the kinetic energy at the beginning was the same as the work, which is 92 joules, which is the same as the maximum gravitational potential energy. And then when it comes back down here, now it's all kinetic energy again. So it's going to be 92 joules again. So we can say the velocity is going to be equal to the square root of 2 times the kinetic energy at that point, which is 92 joules, divided by the mass, and the mass was 12.5 kilograms. And when we plug that all in, we're going to get 3.8 meters per second. So the velocity equals 3.8 meters per second. A boy carries a water balloon up to the top of a ladder to let it drop. The mass of the water balloon, all right, so we have a ladder, we have a balloon at the top of the ladder. The mass of the balloon is 255.8 grams. And then the ladder, so we're at 10.4 feet high. You know what? I'm going to picture the ladder like this because the way they're making it sound is probably a the ladder is probably perfectly vertical like this. How much potential energy does the balloon have at the top of the ladder? So gravitational potential energy is equal to the mass times the gravity times the height. So let's see. They gave us the mass. The mass is equal to 255.8 grams. So we have to change that to kilograms because we have to have it in MKS units. And when we plug that into the calculator, we get 0.2558 kilograms. And divided by 1,000, you could plug it in, or you could just recognize, like, oh, I have to move the decimal 3 points to the left, or 3 places to the left. All right, now we know that the mass, the height, they gave us as 10.4 feet. Well, we need to convert that to meters. So feet, meters, and it's 0.3048 meters in 1 foot. And when we plug that in, we get 3.1699 meters. Right now we have all the information we need. The potential energy, the gravitational potential energy is going to be equal to the mass, 0.2558 kilograms, times gravity, 9.80 meters per second squared, times the height, which is 3.1699 meters. When I plug that all into the calculator, I get 7.95 joules. Okay, so the gravitational potential energy at the top is 7.95 joules. And then if the balloon is released, how fast is it going to go right before it splats on the ground? So if we let go of it, it's going to fall down, right? So I'm going to just mark over here, we found out that it's got the potential, the gravitational potential energy at the top is 7.95 joules. That means down here at the bottom, now it's all been converted to kinetic energy right before it falls. So the kinetic energy there is 7.95 joules. So the kinetic energy, in the end, kinetic energy final, is going to be equal to 7.95 joules. And now we can do the velocity, which is the square root of 2 times the kinetic energy divided by the mass. So the square root of 2 times 7.95 joules, excuse me, divided by mass, which is 0.2558 kilograms. And when we plug all that into the calculator, we get 7.88, and its velocity, so our meters per second.